In 2004 we built this project we called the Solar Bubble Build. We believe it was the first project of its kind in Europe. This project was a liquid bubble insulated greenhouse designed around a concept developed by Richard Nelson. Our primary motivation for building the greenhouse was to protect my wife's tropical plants. We lived in the southeast of England, so it wasn't super cold or anything, but still the plants she wanted to grow wouldn't survive outside. So after approximating how much it would cost to heat a regular greenhouse over the winter, we decided it would be worthwhile looking at some alternative technologies, and we settled on this idea. Whether the project did ultimately save us money is difficult to say, because as the project evolved it became more of a research project rather than just a practical solution to propagating plants in the spring and overwintering Lawrence tender plants. Unfortunately, the project is no longer there. In 2012 we emigrated to America and we had to dismantle the greenhouse because we were on rented land. We did get one video of the greenhouse filling, and we got a lot of build images, so I will go through the images and explain how we put the project together. Before I do that, we should probably just go over some of the key features of the greenhouse and get an overview of how they all work together. Under the greenhouse we dug a large insulated tank which we used as a thermal battery. So during the cold season, when the sun was out, during the day we would run a film of water in the south cavity on the inner skin, and that would go to the thermal mass and charge that during the day. So in this system we're collecting low-grade heat and using the plants as part of the mechanism by which we do that. So to cool themselves, the plants transpire. This essentially involves a phase change from water to water vapor. That heat energy that the plant has transferred to the surrounding air is called latent heat of evaporation. So the warm, humid air inside the greenhouse sees the cooled inner skin and condenses on that skin, and that's another phase change back to water, and when that phase change happens, the heat energy is released and transferred to the film of water running on the other side. I should just say that I'm no scientist and I may have gotten this completely wrong. I welcome people to correct me in the comments if you know better, but this is basically how I've come to understand the system. So during the heating season nighttime operation, we fill the cavity around the greenhouse with liquid soap bubbles. This provides a layer of insulation, but it also enables us to return the collected heat energy we've stored in the thermal mass to the inner skin of the greenhouse. We believe this is an efficient way to return that stored heat. Of course, some of the heat energy will be lost to the outer skin and to the ambient outside air. But when the bubbles are introduced to the cavity, much of the water in the bubble walls will actually drain down as the bubble walls thin, and that water will obviously run to the inner skin, still containing most of the heat energy. When the bubbles are first generated, they're quite wet, but only after 5 minutes the bubble walls become thin and the bubbles look translucent, with a slight kind of blue hue to them, and it's in this state that they have the best insulation property.
You just disappeared, didn't you?
Yeah, I know.
After building the project, we did conduct a few tests to try and get a better handle on how the bubbles were performing as an insulation. It's had a few challenges. One was that bubbles will melt away from a warm source, so we actually used ice to replicate how the bubbles would be in a cavity with on a cold night, and then measured the melt water from that ice, and then from there calculated the insulation value. If there is interest, I can probably go into more detail about these tests in another video. We ended up concluding that we were seeing about 0.5 R per inch, although there were some flaws in our test rig. Richard Nelson's own experiments have indicated that the bubbles have an R value of about 1 per inch. This unit was designed to cheaply replicate a greenhouse environment, and just to simplify the whole mechanics of making the bubbles, and enable somebody to, build two and have one's control without bubbles, and just do a direct comparison of the two structures. Probably about 50% of the materials we used to build the project were reclaimed. We got a set of hoops from a local farmer, and this determined the dimensions of our structure. The hoop steel was a smaller diameter than what I had wanted, so I ended up placing the hoops closer together than what would have normally been recommended to make this structure more sturdy. I managed to get my hands on some old industrial shelving steel, and I used this in numerous places around the build to reinforce and make brackets. To transition from different sized pipes, I improvised these reducers. I managed to find a bunch of insulated stainless steel clad wall boards in a dumpster outside of a factory, and these came in handy, although they were a pain to process. I only had a 4.5 inch angle grinder, and some of the boards had steel facing both sides, so I would have to make 2 cuts with the angle grinder and then cut with a handsaw through the insulation. One downside about using a lot of reclaimed materials is that you can spend a lot of time preparing and standardizing the dimensions of those materials before you can use them. Skinning the greenhouse even single-handedly is fairly straightforward as long as there's no wind. Having the cavity continue around the end wall probably doubled the complexity of the project. If I was going to do it again, I think I would just use solid insulation for the end walls and bubbles just on the north and south side. We originally dug the ditch at the front of the greenhouse on the south side so that I could mount some large solar panels beneath the glazing. In the end, we just abandoned the idea because it was too expensive. To save money, I built the bubble solution return gutters from poly, leftover poly from the skin, but this created issues and problems connecting that poly to the drain system. I ended up finding if I sandwiched the poly between 2 rigid layers of gutter or pipe, this proved to be pretty reliable and leak proof. If I was going to build another structure, I think I would definitely go for a rigid, hard return gutter. I found if I was in the cavity space or working at the top, and if I dropped a screwdriver or a tool, it punctured the gutter at the bottom. So that was, and of course, the problems they had connecting it to the drain system just wasn't worth the cost saving. My first approach to returning the air from the collapsed bubbles back to the bubble generator was to draw the air from the soap gutter at the bottom of the cavity and use a perforated membrane to stop the bubbles from being sucked into that return pipe. Richard Nelson warned me against doing this, and he was right, because it was a terrible idea. The best place to take the air to return back to the bubble generator is the last place to fill with bubbles within the cavity. So my second approach was to use the spine at the top of the greenhouse to create a duct to return the air from above the doors. Finally, I made a tensile poly return duct which seemed to work the best. The material you use to make your bubble screen in the bubble generator has a big impact on the performance of the generator. The first material I used was an open cell foam used in fish tank filters. The second material, which performed a little better, was a type of bug screen. The material that worked the best, however, was a heavy sports woven fabric. In another project, we used this fabric to make bubble generators that produced 3 cubic meters of bubbles per second. Keeping the bubble screen saturated with soap solution is important. To do this, you need either a single or an array of full cone nozzles. If the bubble screen does have a dry spot on it where the solution doesn't reach it, it will produce large voids in the bubble mass. I'm going to make a separate video that goes into the details of the performance of the project and some of the data we collected. This video was just to give an overview of the concept and construction of the build. If you want to see some more videos about this project, please like and subscribe to our channel. I do want to share some ideas and some designs of another structure I'd like to build using the same concept. If there's enough interest, I will certainly make some videos about that.
Shit, Harvey. So your seals aren't very good then?